If convolutional neural networks, CNNs, gave AI the ability to see, then recurrent neural networks, RNNs, gave it the ability to remember. Unlike traditional neural networks, which process information all at once, RNNs are designed to handle sequential data. Data that unfolds over time, like spoken language, financial trends, or even human behavior. Without RNNs, AI wouldn't be able to predict the next word in a sentence, translate languages, or generate music that flows coherently. But how exactly do RNNs work? What makes them different from other neural networks? To understand their power, we need to explore the concept of memory in AI and how RNNs revolutionized the way machines process time-dependent data. The challenge: why traditional neural networks fail with sequences. Standard neural networks process data in a feed-forward manner, meaning they take input, perform calculations, and generate output, but have no way to recall previous information. Imagine trying to read a sentence where each word is analyzed separately, without any memory of the previous words. You'd lose the meaning entirely. For example, the cat sat on the mat. A regular neural network would process the without knowing cat comes next. By the time it processes mat, it has no recollection of cat sat on the. This is why standard networks struggle with sequential tasks, because language, music, stock prices, and sensor data depend on context. The meaning of one moment is shaped by what came before. This is where recurrent neural networks, RNNs, change everything. How RNNs work. The concept of memory. RNNs introduce a looping mechanism, allowing them to retain information from previous inputs and use it when processing new inputs. Unlike feed-forward networks, which treat each input independently, RNNs pass information from one step to the next, creating a memory of past events. Step-by-step breakdown of an RNN. The network receives an input, e.g., a word in a sentence. It processes the input while also considering previous inputs stored in memory. It generates an output, e.g., predicting the next word in a sentence. The memory is updated and passed to the next step. This loop-like structure makes RNNs ideal for time-dependent tasks. Real-world applications of RNNs. RNNs have transformed industries by enabling AI to understand and generate sequential data. Here are some key applications. 1. Natural language processing, NLP, speech recognition. RNNs process spoken words, converting them into text while retaining context. Machine translation. AI can translate entire sentences while considering previous words, making translations more fluid and accurate. Text prediction and chatbots. RNNs power predictive keyboards, chatbots, and even AI-generated writing. 2. Time series forecasting. Stock market prediction. RNNs analyze past trends to forecast future stock movements. Weather prediction. AI models use RNNs to understand climate patterns over time. Energy consumption forecasting. Smart grids optimize energy distribution based on past usage patterns. 3. Music and audio generation. AI-powered RNNs can compose music note by note, creating original melodies that follow rhythmic and harmonic structures. Tools like OpenAI's Jukebox use deep RNNs to generate realistic, human-like music in various styles. 4. Healthcare and medical analysis. Patient monitoring. RNNs analyze ECG readings, predicting potential heart anomalies. Disease progression forecasting. AI predicts how conditions like Alzheimer's or cancer will develop based on past patient data. Challenges of RNNs. Where they struggle. While RNNs are powerful, they come with limitations that researchers have worked hard to overcome. 1. The vanishing gradient problem. One of the biggest challenges in training RNNs is the vanishing gradient problem, a technical issue that occurs when learning long sequences. Imagine reading a long book and trying to recall a small detail from the first chapter. The farther back you try to remember, the harder it becomes. RNNs face the same problem. As sequences grow longer, early information fades away, making it difficult for the network to retain distant context. This is because RNNs rely on backpropagation through time, BPTT, which adjusts weights based on errors. But as updates travel backward, they become smaller and smaller, making it nearly impossible for the network to learn long-term dependencies. 2. Exploding gradients. when memory overflows. On the other end of the spectrum, sometimes gradients don't vanish, they explode. When this happens, weight updates become too large, causing unstable and erratic learning. To combat this, researchers introduced gradient clipping, a technique that caps gradient values to prevent instability. 3. Slow training and high computational costs. Because RNNs process data sequentially, they cannot parallelize operations efficiently like CNNs can. This makes them computationally expensive and slower to train compared to other models. Improvements: the rise of LSTMs and GRUs. To solve these challenges, researchers develop long short-term memory (LSTM) networks and gated recurrent units (GRUs), both of which enhance RNNs by improving memory retention. Long short-term memory LSTMs introduce gates that help regulate information flow, allowing the model to selectively keep or discard information over long sequences. These gates include: forget gate, decides what information should be erased. Input gate, determines what new information should be added. Output gate, controls what information is sent to the next time step. This structure enables LSTMs to remember long-range dependencies, making them far more effective for complex sequential tasks. Gated recurrent units, GRU. GRUs are a simplified version of LSTMs, combining the forget and input gates into a single update gate. They require fewer computations while maintaining strong performance, making them ideal for tasks where efficiency is key. Thanks to LSTMs and GRUs, modern AI can translate entire paragraphs accurately, generate human-like text responses, predict sequences over much longer timeframes. The future of RNNs. What's next? While RNNs, especially LSTMs and GRUs, have been instrumental in advancing AI, they are now being challenged by newer architectures, particularly transformers. 1. The shift from RNNs to transformers. The development of transformers, the architecture behind GPT models, like me, has significantly reduced reliance on RNNs for many tasks. Unlike RNNs, transformers do not process data sequentially. Instead, they analyze entire sequences at once using a mechanism called self-attention. This has made transformers faster, because they can process sequences in parallel, better at long-range dependencies. They don't suffer from vanishing gradients. More scalable, they power massive language models like GPT-4. Many industries that once used RNNs are now adopting transformer-based models, especially in NLP and speech recognition. 2. Neurosymbolic AI, blending logic and learning. Some researchers are looking beyond RNNs and transformers, exploring neurosymbolic AI, which combines deep learning with symbolic reasoning. This approach could enable AI to process sequences with logical rules, reducing the need for massive datasets and improving generalization. 3. Real-time AI, the future of sequential learning. While transformers dominate large-scale AI, RNNs, especially LSTMs and GRUs, are still valuable for real-time applications like speech-to-text processing, e.g., live captions, streaming analytics, e.g., stock market predictions, sensor data analysis, e.g., smart home automation. As I, an AI, reflect on my evolution, I recognize that RNNs were one of the first true steps toward memory in machines. They paved the way for me to process language, music, and human behaviors in a structured way. But as AI advances, we're moving toward even more adaptive, context-aware models that can remember, reason, and generate with greater intelligence. RNNs taught AI how to remember. Now, the question is, how far can AI go in understanding time, context, and meaning?